Hi all. Uh, Starting from this video, we're going to look into graphical representation of complex numbers because we learned about complex number general representation, that is called the Cartesian representation. How a complex number is represented. That's we learned, right? And we discussed different properties of them and what is the modulus of a complex number, what is the conjugate, and so on and so forth. How to multiply, how to divide. So those things we learned and their properties, and we did some questions on that. We will do more questions based on that with time. Right, so now we should focus on the representation. How can we represent a complex number? Now when it comes to real numbers, maybe in grade 6 you learned about real number line, right? What did you use a number line for? A number line is used for representing real numbers. That actually gives you a graphical representation, intuition behind what numbers are, right? So example, in the middle you have 0, 1, 2, 3, minus 1, minus 2, minus 3, right? Suppose you wanted to represent 2, right? So you put a circle here. What does it imply, right? So when you put a circle here, and that means we are pointing at 2 on this number line, right? So you can see that 2 is 2 units away from 0. If you want 3, this is 3 units. This is 2 units away from 0. So you can see when the number gets larger and larger, it becomes more further away from 0, right? So this gives you a sense of the magnitude of a number, right? Gives the sense of the magnitude. Now when you say 2, it is about 2 units away. 3 units away, right? 4 units away. So that gives you a sense, graphical representation. Now if you wanted to represent pairs of numbers, 2 numbers, right? We use Cartesian plane, right? So we have another axis here, right? Y-axis. 1, 2, 3, minus 1, minus 2, minus 3. Right. So any point in this plane, represent 2 numbers uniquely, right? One is the x coordinate and the other is the y coordinate. So 2, 2. If you select any point, suppose this point refers to minus 3, minus 2. So you can see every point in this Cartesian plane represents 2 numbers, 2 real numbers, right? So this point tells you that this point is 3 units away from 0 to the left side and 2 units below 0 downwards, right? 2 units down. 3 left, 2 down, right? 2 right, 2 upward, right? That gives you a sense and direction and all. Now this is how you represent real numbers. Then if you put another axis like this, 3-dimensional space, you can represent each point in 3-dimensional plane is represented by 3 real numbers. So this gives you general sense. Then we use Cartesian plane to draw graphs and all, right? So graph means it's graphical, right? That's where the graph comes from, graphical representation. How 2 variables are related, that gives you a sort of graph, gives you a graphical representation of functions, of numbers, how these are related, different patterns, right? Okay, so what about complex numbers? Can we represent complex numbers on the number line, on the real number line? The answer is no, right? Because real number line is used to represent real numbers only. Complex number is a combination, linear combination of a real and imaginary. Sometimes imaginary part is 0, then complex number is reduced to a real number. But still real number line is not enough to give you a complete representation of complex number. That's why we are in dire need of having a different way to represent complex numbers. Okay. So can we use Cartesian plane? No, not again, because Cartesian plane on the class Cartesian plane, every point is represented by two real numbers. Still we have two real numbers, no imaginary numbers here. Then what should we do? So to come up with representation of complex numbers, we're going to use Cartesian plane, but with a small change. We're going to do a slight change to the Cartesian plane, and you're going to use the same intuition to deal with complex numbers. Let's look at that. Right. So you can see the Cartesian plane on the left hand side, and I have another plane on the right hand side. Notice the difference. Right. X-axis replaced by, because a complex number is a linear combination of real and imaginary. Real and imaginary, they don't mix with each other. So we have to use different axes to represent real and imaginary separately. So what we can do is that we're going to use this horizontal axis, usually named as x-axis, as a real number line, right? Real number line. Then y-axis is replaced by imaginary axis, right? This is called the imaginary axis. This is called the real axis, right? Imaginary, real. So let me write down the words. This is imaginary axis. You don't have to write it down every time you draw the complex plane. These two is enough. IM and RE is enough, right? Imaginary axis. This is real axis, right? Imaginary axis and real axis. Here y and x. In this case, both are real numbers, real number lines. Here we have a real number line to represent all the real components or real parts sometimes. And here we have a vertical line to represent imaginary numbers or imaginary parts sometimes, right? So suppose you have IM and RE, then you represent imaginary numbers on this number line, right? If we have this instead, so don't write this down yet. We have this instead, IM of C and RE of C, then this implies imaginary part of complex number, and this implies real part of the complex number. In that case, you represent imaginary part on the real axis, on the vertical axis, right? So imaginary part is just a real number again, so you know that. Okay, so that there's a distinction between them, but you don't have to worry too much about it. So imaginary axis, real axis. Okay, so let me write down the numbers. So this is I, 2I. Same way. Similarly, we can put this negative I, negative 2I, negative 3I, negative 4I. On the real axis, you have 1, 2, 3, 4, the list goes on, minus 1, minus 2, minus 3, minus 4, this goes on. Okay. Suppose we have this number 3, 2, right? This point refers to a point. This point is a point in the Cartesian plane, right? And is referred by two real numbers, x coordinate first, then y coordinate, 3, 2. Okay. What about this? This is 2I, this is 3, and this point represents a complex number. How do you write complex number? First you write the real component, then the imaginary component. This is plus 2I, so plus 2I, right? Notice the similarities. They are quite similar. Similarities. 3, 2, 3, 2. This is also a Cartesian plane, but it's different because we need to make the distinction between real numbers and complex numbers. So that's why we made the distinction by replacing y-axis with IM and x-axis with RE. Okay, I think you got the point here. It's very simple. It's the same thing. Instead of 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, and the ones are below. we use I, 2i, 3i, 4i, 5i, or minus I, minus 2i, minus 3, minus 4i, like this. Okay, so that's the all difference. Now let's look at some examples on this. Right, so we'll represent these numbers in the Cartesian plane. It's very simple. First number, 4 plus 2i, 4 plus 2i. Find 4 on the real axis. 4 is here. 4 is here, right? Then 2i, where is 2i? This is 2, and the line and the point that is intersected by these two lines gives you 4 plus 2i. 4 plus 2i. Very easy. This is Montessori stuff. It's very easy. Okay, should be able to represent these. 3 minus, now notice here. Yeah, okay. 3 minus 4i. Find 3 here. Minus 4 on the imaginary axis, somewhere here. So should be somewhere around here. These are just sketching, right? Only sketching. Okay. So this one is 3 minus 4i. This point is 3 minus 4i. Okay. Next, minus 1, minus 2i. Where is minus 1, minus 2i? This point, minus 1, minus 2i. Right. Then minus 4 plus 5i. Minus 4 here, plus 5i here. So it's somewhere here. Right. This is minus 4 plus 5i. So you can represent as many complex numbers as you want for just exercises. Get used to this representation because this is a very basic thing, right? Very basic thing. We'll be using Argand plane because in past web questions they have asked about representation of complex numbers and different graphical exercises on complex numbers. So we'll be using this a lot. Right. So now notice here that in this region, all real numbers and imaginary numbers, both real and imaginary numbers are positive. Not number. Both real part and imaginary part are positive. Both real part and imaginary part are positive. And you can see if I take this point, this is 1, 5i. 1 is positive, 5 is positive. Here 4 is positive, 2 is positive. What about in this case? In this region, all the real parts are negative, but the imaginary parts are positive. 5 is a positive number. In this region, both real and imaginary parts are negative, right? Minus 1, minus 2. In this region, real part is positive, imaginary part is negative. 3 minus 4i. Imaginary part is negative. So similar to Cartesian plane. So similarly, we can define quadrants in complex plane as well, right? So there are 4 quadrants, and we'll look into that next. Right. So let's take a complex number, general x plus iy, where x and y are real numbers. So x and y, x is the real part of complex number, y is the imaginary part of the same complex number. Now you saw that real part and imaginary parts are both positive in the first quadrant, right? In other way, if you want to know where your complex number lies, just by looking at it, in which quadrant it lies, you should confirm that you should confirm the signs of the imaginary parts and complex parts, right, together, right? If your complex number has positive imaginary part and real part, then it's in the first quadrant. So x is positive and y is positive. Sorry, x is positive and y is positive in the first quadrant, right? the second quadrant, what is negative? The real part is negative. So x is, this is our second quadrant, x is negative and y is positive. Third quadrant, both are negative. So x is negative and y is also negative. The fourth quadrant, x is positive, real parts are positive, but imaginary parts are negative. So this is the quadrant 2. So what about on the axis? On this axis, imaginary part is 0. Imaginary part is 0 on this axis. On this axis, real part is 0. Right? On this axis, if your complex number is on this axis, which means the real part is 0. If your complex number is on this axis, that means imaginary part is 0. Okay? So please keep that in mind. Right. So we learn how to represent complex numbers in Cartesian complex plane or Argand diagram. So it is also called Argand diagram. I forgot to mention that. Argand diagram or complex plane. Either words is fine. Right. So this is how we represent a complex number. If you know the real component and the imaginary component, you can represent the complex number. It's same thing as you do with Cartesian plane. It's the same thing. If you know the x coordinate and y coordinate, you can represent any number. Similarly, if you know the real component and imaginary component, you can represent any complex number. Now this representation is good for representing complex numbers. This is called the Cartesian representation. It's good for representing complex numbers and to do certain things, simple things. But when it comes to, for example, let me show you, here let's take z is x plus I, y, where x and y are real numbers. Suppose you want to expand this one. Now 1 plus I, you don't have to write this down. 1 plus I squared. So very easily you can find the answer, right? So this is 1 squared plus 2I plus I squared. I squared is minus 1 plus 1 is just, this is 2I. That's okay. What about 1 plus I? If someone asks you to find this 3, then what do? Use binomial expansion. So 1 cube plus 3 1 squared I plus 3 1 I squared plus I cube. This is 1 plus 3I minus 3 minus I. Minus 3 minus I. So answer is minus 2 plus 2I. This is also easy, right? Find, determining the powers of complex number. This is the same complex number, 1 plus I raised to 2. 1 plus I raised to 3. So if you are asked to find 2 raised to 3, you know this is 8. Similarly, you should be able to find powers of complex numbers. Now, what happens if the power is higher? Suppose you wanted to find 1 plus I raised to 10. Still okay. Still okay, you can determine it using the binomial expansion. But what if this is 1000? This is 100. What if this is 1000? What are you going to do then? Right? You can have to spend your whole lifetime calculating this. Who knows? We can't do this, right? So sometimes you might wonder, we already have a representation, so why do we need a different representation? This is the reason, right? So using Cartesian coordinate or Cartesian representation will get into troubles when we determine powers of complex numbers, right? Positive powers or negative integer powers. Okay, and multiplication. When you multiply complex numbers, you get into trouble. When you divide, again you get into trouble. But there's an easy way, right? If you change the way you perceive complex numbers, that means if you change the way you look at it, right? If you change, if you can come up with a different way to represent complex numbers, then maybe you can deal with these problems, these issues. Right? This is where polar representation of complex numbers comes to play. Polar representation. Right? This is why polar representation is introduced, this process. Now we'll look into polar representation, and let's, after that, after theory part, during the class sessions, we'll look into more problems with regard to this. First of all, I'm going to introduce polar representation, then I'm going to do a couple of problems that involves polar representation. So you should know how to go from these two systems. How do you go from Cartesian representation to polar representation? I still didn't introduce what it is. Okay. Right. So you can see this is how we represent a complex number. Right? If you know real part and imaginary part, you can represent complex number. Also, there's another way to represent it. How? If you know the distance of the complex number from the origin, if you know the distance, we call it r. This is the distance. And the angle it measures with the positive real axis. The angle it measures with the positive real. I will get to that. So we know this angle, right? Angle it measures with the positive x-axis, theta. Then you can represent x plus iy or this complex number using these two data. Because if you know how far it is away from the origin and the angle it measures with the real axis, then using these 2 points you can uniquely describe this point, right? This complex number. Now let's see how to represent them. Now if you look at it, this is a right angle triangle, and I can replace x and y using these two variables. So r is the distance, theta is the angle. Okay. So r cos theta is equal x, and this distance r sin theta. So this would be your imaginary part. R sin theta is what? Now replace these two with these definitions. So that gives us z equal r cos theta plus I times r sin theta. So you can see r is common to both these terms. So let me factor out r. Then we get cos theta plus I sin theta. Very easy. Z. So this is called polar representation. Polar representation of complex numbers. So when you do higher studies, we're going to use more abbreviated representation of complex numbers using polar coordinates. So these are called actually polar coordinates, r and theta. These are called polar coordinates. So when you move above the ladder in the academic path, then you will learn about spherical coordinates, cylindrical coordinates, polar coordinates, everything, right? So for your scope, you have only polar coordinates. This is the basic one. Okay. Now let me write down that representation as well, more abbreviated, short form. Now writing this is not always easy, but you are going to use this representation only, right? So what I'm going to write here, never use it until you go to university. So r cos theta, I can write r cis theta. It's the same thing, r cis. So this c represent cos, I represent I, s is for s in sin theta, right? So this is not important, right? It's not important. Let me just don't use this. Don't use this. Okay? Use this always. So this is called the polar representation of complex numbers. Now you can see in a complex number you have r, which is the distance from 0 to that point, and theta. So cosine and sines are just functions, right? Theta is the angle it measures with the real axis. How much it has rotated from real axis. Okay. So let's define. There are special names are given for these two variables r and theta. So let's look into that next. Right. So in Pythagorean theorem, you know that the r is the hypotenuse, x is the adjacent to theta, and y is the opposite to theta. So r is square root of x squared plus y squared, that we know. So what is square root of x squared plus y squared? We have already defined it. This is actually the modulus of CR. So now you know why we define modulus first in the initial stage, right? පළවෙනි වීඩියෝ එකේ දෙකේ වගේම මම මේ මොඩියුලස් එක කියන්නේ මොකද්ද, conjugate කියන්නේ මොනවද, ඒවා මම introduce කරලා දුන්නේ මෙන්න මේ හේතුව හින්දා. So this is why we represented modulus. So now you know what modulus actually means. So modulus of a complex number is actually the distance. It's actually the distance from origin to that point. Okay, so that is the distance from origin to that point. Okay, now we know the intuition behind modulus. Okay, r. Then theta. How do you find theta? So tan theta is y divided by x. Y divided by x. So in other words, what is y? Y is the imaginary component of z, and x is the real component of z, tan theta. Okay. So theta is therefore tan inverse. We can use both definitions, y over x, or in general this is tan inverse IMZ over RD of C. This is general. So this is important. You should be able to determine these when a complex number is given. Now you know how to go from x and y. Now x and y, when x and y is given, you know how to find r. It's just the modulus. Then what about theta? You just take tan inverse of y divided by x. It's theta. Now we know how to go from x plus Cartesian representation to polar representation. Okay. So special names are given to these. Now you know already what r is called. And what about theta? Right, so let's get into that as well. Right, so r is the modulus of z, that you know. So what about theta? Theta is the angle it measures with the positive real axis. Now you can measure angles anti-clockwise or clockwise. So we usually use anti-clockwise measurements because we define anti-clockwise measurement as positive angles, right? If you measure it clockwise, then that is considered a negative angle. Okay, so keep that in mind. Now depending on the signs and magnitudes, the angle, the name given for the angle is defined in two different ways. Now theta is called in general argument of c. Theta is called the argument of c. Now it's defined in two ways. This is very easy, don't get confused with this. Now you can see here, in short form we write it like this: simple A R G. This is to say argument of C. Simple A R G. Right? So we call argument. So if you are asked to find the argument of the complex number and they use simple A, you can say simple A for that. Your angle can be a positive angle or any angle, can be any angle, but basically we restrict ourselves to this. When you get into university, you will see why we use different angles. I mean, any angle is possible. When theta is between 0 and 2 pi, that means anti-clockwise rotation, one complete rotation from 0 to 360 rotation. If we use any angle, any anti-clockwise angle to refer uh, to represent that complex number. So that is called this argument of C. Notice in front you have simple A. Now if we use capital A, then if they ask you to find argument of complex number and they use capital A, then you have to give the angle, right, like this, from positive pi to negative pi. So what does it mean? From positive pi to negative pi means first two quadrants. So you can see we have 4 quadrants. This is first two quadrants goes from 0 to pi. 0 to pi. And third and fourth quadrant can be represented by negative angles, negative pi, right, negative pi. So I'll give this to you soon. You can see here the difference. Now if we use this definition, you can have to use positive angles to represent it. If you use this definition, if your complex number is in first and second quadrant, then it's no different. It's the same thing like this. If it is in third and fourth quadrant, you can have to represent that complex number using a negative angle. That's the only difference. So note here, so the angle is defined in two ways. You can see depending on the magnitude and sign of the angle. So if in the question it is not specified, so usually they are asking for this. Usually in general they are only looking for this. If it is not specified, always use this definition, right? Always use this. So we're gonna look into this definition mostly, and I'll refer to this whenever it is appropriate, right? So why is it different? Now this argument is called principal argument. Principal or principal value. Principal argument. Right? This is called the principal argument. Okay. So those are the differences, and you should learn these definitions with regard to polar representation of complex number. Now we'll make a small note on these two. Right. So these are the two differences. The major difference between them. Simple argument, right? Simple A. This argument is basically the angle, right? Angle, it measures with respect to real axis. Angle it measures with respect to real axis, anti-clockwise, right? Anti-clockwise. This is anti-clockwise representation. You can see anti-clockwise. So here you can see IM, RE. Here anti-clockwise, and third and fourth quadrant. So this would be second quadrant, this is first quadrant, third and fourth quadrant. Any complex number that is within third and fourth quadrant is measured with clockwise angle, and this angle is called the principal argument of the complex number. This is called just the argument of a complex number. Okay. Right. So let's make it clear on the argument further. Now, if you look at any complex number in the first quadrant, right? First quadrant, the angle it makes with the real axis, it's acute angle. It's an acute angle. So you can see here this angle is between 0 and pi by 2. It is between 0 and pi by 2. So if C, this is very important. It's very important to get clear idea on this before we move on to examples, because if we have a clear understanding on this, if we follow what I say, then it is very easy to go from Cartesian representation to polar representation. Then see argument with simple A, argument is theta actually, argument is theta is between 0 and pi by 2. So obviously, if your complex number is in the first quadrant, you should know this is how you make sure your answer is correct. How to make sure your answer is correct. First of all, you have to locate the complex number. You have to know where the complex number lies. Just do a small sketch and find. Okay. Then, when you know in which quadrant the complex number is, then you know what is the argument should be. Right. So if you find a different argument, then you know that you are wrong. Okay. So argument with simple a should be is the angle between 0 and pi by 2. Similarly, the principal argument which varies from plus pi to negative pi, that is also between 0 and pi by 2. If you are asked to find the principal argument, it's the same thing, right? So principal argument and simple argument, just argument with simple a, the same thing if your complex number is in first quadrant and second quadrant. So in this case, simple ARG of C is equal to capital ARG of C. Okay, so this is the first thing. Now let's see what happens when your complex number is in second quadrant. Right, so if your complex number is in the second quadrant, your real part is negative, imaginary part is positive. If that is the case, you can see this is your argument, right? This is the angle. This is actually the angle it measures with the positive real axis, right? So this angle should be, so if you are in the second region, the angle should be between this, that is 90 and 180. So 90 and 180. So your argument should be between 90 and 180. 90 and 180. Similarly, principal argument is also between 90 and 180. So in this case also, simple argument with simple A is equal to principal argument, right? In this case also, principal argument is equal to the argument of C. So let's look at what happens in right. So if your complex number is in quadrant 3, third quadrant, so please make the changes, right? And also draw the diagram correctly. Now, if it is in the first and second quadrant, I didn't have to make the distinction between argument with simple A and the principal argument. They are both equal, right? So now I'm at a point where I can make the distinction. Because when it comes to principal arguments, if you are in the third and fourth quadrant, the angle you are measuring is with respect to real axis, but it should be clockwise rotation, right? So notice here that I use two different ways to represent. If you use the clockwise rotation, which you usually use, right? If it is not specified, you have to stick to this rule. This is the argument. So that's why I mentioned theta equals argument with simple A, right? So if you use clockwise rotation, I use different color and different angle here, and this angle is the principal argument of C. So notice here the difference. Now your argument is from pi to 3 pi by 2. So if you are in third quadrant, this should be 160 and this should be 270. So pi to 3 pi by 2, the argument should be an angle between pi and 3 pi by 2. Principal argument must be between minus. Now if you measure it clockwise, this position is minus pi by 2 and this position is minus pi, right? So it should be minus pi by 2 to minus pi. So notice here in this case, argument with simple A is not equal to principal argument. So principal argument is different, but the angle wise they're same thing. Because sign tells you whether it is clockwise rotation or anti-clockwise rotation. The both angles gives you the same position, but you are looking at it differently. That's the only difference. Okay. Next, fourth quadrant, right? So if you are in the fourth quadrant, right? So if you measure the angle with respect to real axis anti-clockwise, That is called the argument, right? Argument with simple a. Okay. So in this case, your angle should be between 3 pi by 2 and 2 pi, 270 degrees and 360 degrees. Okay. So 3 pi by 2 to 2 pi. So it should be an angle between those two angles. And if you are asked to find the principal angle, it should be a negative angle. Principal angle is a negative angle, that is between 0 and minus pi by 2. See, 0 and minus pi by 2. In this case also, argument with simple a is not equal to the principal argument. So you notice the distinction is made when the complex number is in the third and fourth quadrant. That is where you have to be careful. If you are in the first and second quadrant, no distinction is made between the two. Okay, right. So let's try to do some examples, and along the way I will make the distinction between these. Right. So convert the following complex numbers to polar representation, into polar representation. Right. So the complex numbers are given using Cartesian representation. So going from polar to Cartesian is easy. Going from Cartesian to polar is a bit difficult. It's not that hard, it's a bit difficult. We have to be cautious. Now look at this. This is the first thing you do. Keep in mind, the first thing you do is to locate your complex number, to figure out in which quadrant your complex numbers lies. That is the first thing. Now you can see 1 plus I. This complex number, real part is positive, imaginary part is positive, then it must be in the first quadrant. If it is in the first quadrant, your angle must be an acute angle, theta. Okay? An acute angle. So you know that principal argument and the normal argument, they don't have any distinction between them. And this is R. So if you want to represent this complex number using polar representation, you need to know what R is, you need to know what theta is. R is very simple. This is the definition. So this is 1 square plus 1 square. What is this? Root 2. See how simple this is? So R is root 2. Very simple. What about the argument of the complex number? Argument is the angle theta. So we use theta for the polar representation, but you should know what argument is. Because especially when we are dealing with complex plane problems, we can use this name, right? So theta, tan inverse y component, y, so imaginary component, this is 1, x is also 1. So what is tan inverse of 1? Tan inverse of 1 is, when is tan equal to 1? 45, pi by 4. So now we know the angle and the modulus, therefore polar representation 1 plus I can be represented by, or we could say polar representation of the complex number is root 2. So let's say this is equal to C. Let's put C equal, therefore Z equals root 2 within brackets cos theta. Theta is pi by 4 plus I sin pi by 4. See, very simple. Very simple. If your complex number is in the first quadrant, it's very simple. Okay, right. So this is it. Now this is the conversion between the two complex numbers. So here we converted 1 plus I into root 2 cos pi by 4 plus I sin pi by 4. This is the conversion. Should also be able to go from here to here. Conversion. Okay, so we'll do couple of exercises, so until you get used to this. Right. So next one, minus 1 plus I. So I just changed the sign, that's what I did. complex number. Now minus 1 plus I, real part is negative, imagined part is positive, which means it should be in the second quadrant. If your complex number is in the second quadrant, you don't have to make a distinction between principal argument and usual argument. But you need to find theta. So we'll get into a problem here also. Right. So R is what? The same thing, component. This is minus 1 squared plus 1 squared. Minus 1 squared is just 1. It's the same thing. So the modulus is root 2. Again, modulus is root 2. What about the argument? Argument, when you find argument, theta, this becomes tan inverse. Right? So let me not put theta first here. Let me just find tan inverse, because what you are getting is not theta. So let me find what tan inverse y over x is first. So this is tan inverse. Y coordinate is plus 1, right? Imaginary component is 1 divided by minus 1. What is this? Tan inverse of minus 1. Tan inverse of minus 1. Okay. So what is tan inverse of minus 1? Tan inverse of minus 1 is minus pi by 4. Minus pi by 4. Now what is minus pi by 4? Minus represents clockwise rotation. Pi by 4 is 45 degrees. So when you use this definition, math says your complex number is in first quadrant, because only in first quadrant you get negative acute angle. Negative acute angle occurs in the first quadrant only. Correct? Right. So this is not telling you the truth, because we know for sure that our complex number is in the second quadrant. Right? So this is what you do. If in second quadrant now you are getting a negative angle, right? Please keep that in mind. It only works if it is a negative angle, otherwise then we have to use a different way to represent it. So it's fine. So what you're getting is this angle, right? Pi by 4. This should be pi by 4. So this angle should be 3 pi by 4. What I'm doing is that argument, all you do, this angle plus pi. You add a pi. If you are in the second quadrant and you find a negative angle, if you get that right? So negative must be there, otherwise it won't work. Negative angle, all you do is add a pi to it. Just add a pi. It's the same thing, right? This should be pi, and this angle theta must be then pi minus this angle. Pi minus this angle. It's the same thing. So what do you get? You get 3 pi by 4. So if you know how to measure this angle directly, then use that method. That's totally fine. Okay. Now this is the argument. So you know that this argument is also equal to the principal argument. If you are asked to find the principal argument, it's the same thing. Okay. Because in first and second quadrant there is no distinction. Now you can write this complex number in polar coordinate system, root 2 cos 3 pi by 4 plus I sin 3 pi by 4. 3 pi is the same angle. Okay, so keep in mind. So I will give you a note on this later, right? I will give you a note on this later. Okay. Right. Thirdly, minus 1 minus I. So minus 1 minus I, definitely it is in the third quadrant. If it is in the third quadrant, your normal argument must lie between pi and 3 pi by 2. And there is a distinction between this argument and the principal argument. So principal argument must lie between minus pi and minus pi by 2. So we're going to find normal argument here. That's it. So later on we'll get to principal argument. So modulus or R, it's the same thing. Root minus 1 square plus minus 1 square. Minus 1 is a component. This is again root 2. I'm having the same number, so it's easy for me. Right. You can see how easy to find the modulus. Then tan inverse of these two. Tan inverse. Okay. So what is this? Y is the imaginary component. Imaginary component is negative 1. Real component is also negative 1. That gives me tan inverse of 1. Tan inverse of 1 we found that is pi by 4. Tan inverse of 1 is pi by 4. It's a positive angle. So now you know your complex number is in the third quadrant, but math says argument is pi by 4, acute angle. It says it is in the first quadrant. So there's a confusion. So no need to worry. If your complex number is in the third quadrant, your argument, how do you get the argument from this? You get the argument from this by adding this to pi. That's it. Add pi. So pi by 4, this is the angle you are getting actually. This is the angle. So from here to here you get pi. Pi plus pi by 4 gives you the complete angle. Okay. Add a pi. If in third quadrant, add pi. So this should be 5 pi by 4. Now we can write down the polar representation. Root 2 cos 5 pi by 4 plus I sine 5 pi by 4. Okay, this is the representation. And finally, let's look at a complex number in the fourth quadrant and we'll make a summary on this. D 1 minus I. 1 minus I, real part is positive, imaginary part is negative. It must be in the fourth quadrant. So the modulus is the same thing, 1 squared plus minus 1 squared. So the answer is root 2. Easy. This one tan inverse of y over x. Or imaginary component over real component. Whatever you like. So this is tan inverse of imaginary component is minus 1. Real component is plus 1. What is this? Minus 1. So tan inverse of minus 1 is pi by 4. Minus pi by 4. Now it tells us the same thing. It tells us true. Your complex number is in the fourth quadrant. It also says minus pi by 4 refers to minus pi by 4 refers to a complex number in the fourth quadrant. Negative rotation. Okay. This is telling the truth. But usually when you are asked to find the argument or when you are converting it complex number into polar representation, you can use positive values. I mean positive angles, theta. You need to find this. If you are asked to write it in simple arguments, right? Using simple argument formats, then this answer is correct. Then you don't have to make any changes and you can just write down the answer. But you have to find the argument, this angle with respect to positive real axis. So here's the thing. This is what you do. If in fourth quadrant, right? If we have another way to figure this out, that is also fine. So the angle we see here is this, right? So you should be able to get the angle here. It's very easy. Right. So what do? You add, in this case, you add 2 pi, not 1 pi, you add 2 pi to this to get the right argument. So if we add 2 pi, this would give you 7 pi by 4. It would give you 7 pi by 4. Therefore, polar representation is root 2 cos 7 pi by 4 plus I sine 7 pi by 4. Right? Plus is there. Okay. So keep in mind how to go from here to here. So if you want to go from polar representation to Cartesian representation, all you have to do is to multiply this, but expand this and get what is cos 7 pi by 4 sine 7 pi by 4. If you expand it out and simplify, you get the answer. It's very easy to go from here to here. But going from here to here takes time. So now let's put a summary. If you stick to these steps, then it is very easy to figure this out. Right, so here's a summary. When you're going to convert from Cartesian representation to polar representation, very first step is to locate the quadrant, or locate the complex number. Where's the complex number? In which quadrant it lies? Locate the quadrant, that's the first thing. So you make a simple sketch and find where it is. That's it. Second step is to figure out the argument, right? So modulus can be figured out, that's fine. I'm not gonna point that here. Step 2. So depending on the quadrant, your argument, you have to make certain changes to your argument. So if you are in the first quadrant, no need, use the definition. So find y and x and get the tan inverse value. Right? This will give you an angle. If your complex number is in the second quadrant, then what do? You add pi to this. Pi plus tan inverse of this one. Pi plus this. Right? If you are in the second quadrant, you just add pi to whatever you get. So notice here, this would be negative, right? So this would be negative, definitely negative angle. So if you are in third quadrant, same thing, you add pi. If you are in third quadrant, this would be positive, definitely positive, right? Here this would be negative value, here this would be positive value. Okay, so I'll sign nature, let's say nature of tan inverse, so let me point that out as well, so you can make sure sine of tan inverse y over x, right? So here the sign is positive. You don't have to notice this one. This is there for your survival, right? Supposed to. So in this case, this is negative. Sine, right? Not the sine of the angle. Sine of tan inverse of y over x. That's it, right? So if you think you would confuse this with the sine of the angle, then don't write that, right? In this case, it would be positive. In this case, it would be positive. So if your angle is in the fourth quadrant, this is different, right? For this and this, you add pi. In this case, you add 2 pi. Keep that in mind. You add 2 pi to it. In this case, sine of tan inverse of y would be negative. So this is a summary. Okay, this is a summary. Right, so if you want summary conversion, let's put another step. 2 and this would be 3. Find modulus. Then this is complete. Right? Z modulus is equal to R. Then locate this one, get the argument. So this is it. Okay, this is it. So go through this, right? Get this in deep and do some exercises. So I will list out some complex numbers so that you can do them as homeworks. Try to convert them and let's see the answers you get during the class. Okay. Right. So do these examples as homework. Try to convert them. And see if your answers matches. So I'm gonna write down the converted value, right? So pause the video here, try to do this conversion and check your answers. Right, so these are the answers. So the modulus is 2, right? Find the modulus, this is 2, and the angle, this is in the first quadrant, so the angle, when you find tan inverse, right, y divided by x, you get pi by 3. So use the same angle. Now this is in the third quadrant. Third quadrant means, so what is the modulus? When you take the modulus, it is 1. So I'm not going to put it here. Angle tan inverse of y divided by x is just 1. Right? It's just 1. So you get pi by 4. If it is in third quadrant, then you get pi. So pi plus pi by 4 is 5 pi by 4. This is in fourth quadrant. Modulus is again 1, so I'm going to point out here. And the angle is negative pi by 3. Negative pi by 3. So if it is in this fourth quadrant, you add 2 pi. If you add 2 pi to this, you get 5 pi by 3. Right. Similarly, here it is also in the fourth quadrant. The modulus is 4 root 2. Find it out. And the angle would be negative pi by 4. When you calculate it, would be negative pi by 4, but if it is in the fourth quadrant, you add 2 pi, right? If you add 2 pi, you get 7 pi by 4, right? So that's the end of this video. Please go through them. If you have any questions, please ask. Thank you.